Okay, thank you, Thomas, for the introduction. And hello, everyone. I'm going to present our dry work on the building compact encryption based on the Module-NTRU problem. So first, I'd like to give a quick overview of our results. If you know, in case of Encryption 3, there's a very compact encryption called NEV based on the ring RW and the NTRU. So they can achieve a very small ciphertext size, so even smaller than the one by a pilot scheme such as NTRU, NTRU prime, and Kyber, as you can see in the table. And in this work, we try to propose another candidate based on the module version of LW and NTRU. So we provide instantiation for both IND and one-way CPA security. And for our IND CPA1, we can achieve quite compact ciphertext, but not as compact as NEV, but better than Kyber, NTRU, and NTRU prime. And then for our one-way CPA1, we can eventually reach the same ciphertext size as NEV, and also with the parameter for the security level 2. So this also fills the gap left by the NEV scheme. So this is our main result. And for the roadmap, I will start by presenting the two assumptions, the two underlying assumptions of NEV. So namely the ring learning with error and NTRU. Then follow with our two design based on these two variants of Module-NTRU. At the end, I will conclude with a few questions for future work. So first, the learning with error, as you have already been very familiar, proposed by Regif in 2005. This problem essentially asks to solve a noisy equation linear system. So the matrix A is completely random, so as the coefficient of this equation system. And the second component is A times the secret S of this unknown variable plus some noise factor E. And other than the search variant that you ask to find the secret S, you also have this decisional variant that asks you to distinguish A and A times S plus E from random. And later, for efficiency reason, as you might know, structure variant of it has been proposed, such as by Staley and Nutt in 2009 as polynomial RWE, and by Lubasevsky and Nutt as this ring RWE. So now the sample is defined over polynomial. If you further view the polynomial product in matrix vector form, so you can view it, for example, as the rotation matrix of the first polynomial times the coefficient vector of the second polynomial. Then you can also view this sample in matrix vector form. So now this matrix A is not completely random. So it has this particular structure depending on the rotation matrix. And here, if you consider the most familiar, most well-known power of two cyclotomic ring, so this rotation matrix has this so-called anti-cyclic structure. So this is about the first problem. And the second problem is the well-known NTRU problem proposed by Hofstede and Nutt in 1998. So now the sample is given as this H as the division between two polynomial of small coefficient, also G and F. And here I try to expand the rotation on the right-hand side. Okay. It also has two variants. So the search variant asks to recover these two small polynomial G and F, and the decisional variant asks to distinguish this H from random. So now we can review the NEV scheme. So the public key is exacted NTRU instance, which is indistinguishable from random under NTRU assumption. Then the encryption is simply to mask the message with the ring LW instance, which is again indistinguishable from random if we assume ring LW assumption. And the main technique to achieve a very compact ciphertext for NEV is to use this so-called double encryption technique, which was already considered in another scenario. So this is the first time they consider it in the NTRU-based encryption scenario. Okay. So here, concretely, given a message M of degree n over 2 minus 1, where n is the ring degree, then there is room not only for the message, but also a copy of it. Right? So now you can not only put the message to the first part, so the lower degree part, but also a copy of it to the higher degree part. If you are not very familiar with this technique, you can simply imagine that if you have one position with the over large error, so the probability can be significant. But if you have two positions, with both of these two positions having a over large error, then the probability will be reduced significantly, right? So now you can use two positions to decode one same single bit. So this helps to improve the noise tolerance of the scheme. And this is how they achieve the very compact ciphertext, even with the very a desirable decryption error, let's say smaller than 2 to the minus 128. So this is about NEV, but as you already seen, it has a major issue that it only provides 2 security level, so 1 and 3. So this is mainly due to their use of this power of 2 cyclotopic ring. So the ring degree jump between power of 2, as you can see, 512 and 2024 correspond to level 1 and level 3, but not the intermediate one. Such an issue was already addressed by Channel and not in 20 in the scenario of signature. So their solution is to use the so-called module version of N-TRU. So instead of using a sufficiently large ring degree, they choose to reduce the ring degree. So this it sacrifices a bit efficiency and also introduce an extra parameter which called module rank K. So the problem size now determined not only by the ring degree, but by the product between the ring degree and the module rank K. So as you can imagine, we have more choices now, as we can play with one more parameter. So now, other than the 2 parameters we have at the beginning, now we have also the intermediate one, the 76A. And this is also the main idea to move a schema from N-TRU to module N-TRU, and it has been very successful for the Falcon signature. So its module version is much more efficient than Falcon signature for some intermediate security level. And now, given NEV in the N-TRU, so we wonder if we can apply similar thing to NEV to have a module version of it, such that we can have a more compact ciphertext size for the intermediate security level. Because in the NEV scheme, they claim that they can use as they're so compact, so they claim that even for security 2 application, they will simply just use a security 3 parameter. But we think it's still more desirable if we can design a parameter for this intermediate security level, more compact. So this motivates our work. And before we go to our first design, I'd like to just quickly go through this module version of LW. So it was initially considered by Barkowski and Nutt in 12, and later formally studied by Longgrass and Stelle in 15. So now the matrix A is not completely random, as you saw for ring LW, but with this locally structure. So it's you can imagine it's less efficient, but provide more parameter choices. So this is our first design. So the public key is exactly the module N-TRU instance. I want to mention that in channel 20, actually they also provide an encryption, but in their scheme they use a matrix H. But here, as we aim for very compact ciphertext, and we also found it more beneficial to use a vector H. That's why we have chosen to use a vector H instead of matrix H. And the encryption is just simply to mask the message with the ring LW, now with the module LW instance. And as you can see now, we have only a single ring element C in the ciphertext C, but we have a matrix F. So how to decrypt, we need one more observation, which is that the product between the matrix F and its adjugate matrix equal to its determinant times the identity matrix. And if we time both sides with H, as H equal to G transpose times F inverse, so F inverse and F, they cancel out. So we are remain with this G transpose times the adjugate matrix. And on the right-hand side, we have determinant F times H. With this relation in hand, now we can use determinant of F instead of entire information of F to decrypt. We can simply use the determinant times C, and the result can be regrouped into 2 parts. We can further simplify the first part using this relation that we have in hand. So the determinant F times H equal to the G transpose times the adjugate matrix. And now, as we know at the beginning, the F we choose has small component. So its adjugate matrix, we have relatively small component. So everything will be over integer. So modulo P will leave us this, the only term M times the determinant of F. Then we can use it to simply distinguish M equals 0 and M equals 1. So this is our first design. And we would like to thank to the reviewer for pointing out that now as we only need to use determinant of F to decrypt, so recovering the determinant of F, will it be easier than recovering the entire information of F, right? So this seems to be a real issue. In order to tackle with this, we need to look closer into the relation that we have in hand. So here, for simplicity, I use F hat to denote the determinant of F and G hat to denote the G transpose times adjugate matrix of F. then the relation can be represented in this figure form. If we focus on only one single equation in this equation system, it's exactly like an original untrue instance, right? And with our parameter, such instance is hyperable to have only one unique solution. So to solve only one single equation already provide us the F header, therefore the determinant of F. So it seems it really helps. But for our parameter, you might notice that the determinant of F also have a norm much larger than the norm of each component in F. So it's multiplicatively larger related to the rank of F. So at least for our parameter setting, the cost of recovering the determinant of F using this way, or by recovering the full F with the standard, for example, the primal attack, the costs are comparable. So eventually it does not really help. So for parameter selection, we try to use power of 2 ring, but actually we did not get up with a very good parameters. That's why we use NTTRU types of ring for more choices for the ring degree. But I want to explain why power of 2 cyclotomic ring does not help, because for example, for the level 1 security, if we use a power of 2 cyclotomic ring, so we need to reduce the ring degree from above 300 to 256 probably. That will force us to increase the rank. But if you remember, we use the determinant of F to decrypt. So a larger rank means that we have a significantly larger determinant of F for the decryption. So that will lead to a significantly larger ciphertext. So that's why we have used NTTRU type ring for the instantiation of our first scheme. But unfortunately, we cannot achieve as compact as NEV for the first scheme, so it seems not successful. That's why we moved to our second design based on this so-called vectorial Module-NTRU. So now, as you can see, so this problem first is initially considered by Bai and Nat in 22, and later generalized by Gardner in Pico Crypto last year. So in this problem, the vector H become a matrix, and the matrix F become a vector. Okay, so it's like a dual form of the original NTRU. And before I move to the design, I would like to simply explain how to select such an instance. So first, you need to randomly generate the bottom part of H except the first row, and also F and G from designated distribution. Then you can compute the first row deterministically using F, G, and the bottom part of H. And one more remark is that we can further save the storage. Instead of saving the whole matrix H, we can use a seed to generate and store the seed instead of storing the full H. Okay, so our second design is follow the same idea as the Gardner in 23, but with different embedding for the message. The main reason is that we view this problem more like an NTRU problem, and Gardner in their paper, they view the problem more like a LW problem. So we also provide different parameter selection. And now the public key is again the vectorial Module-NTRU instance. Encryption is again to mask the message with the module LW sample. And the decryption is much simpler. You can simply do the inner product between the F and the ciphertext vector C. And then you can again regroup into 2 parts. Simplify the first part using our relation in the key journal. So everything will be small as G, F, R, and E are all small. So modular P will leave us the only product between F and the O0M. Yeah, here I would like to mention that for the message polynomial, we only put to the last slot of the ciphertext vector, but leaving all the remaining place to be 0. So this is our second design. One more remark is that so here as we introduce an extra module rank K, so we can use a reduced ring degree. So the noise contributed to the decryption by the message compared to NEV will be smaller. But for IND-CPA security instantiation, it's still not as compact as NEV. And we think the main reason is that we did not apply the double encryption technique because we reduced the ring degree. For example, the message polynomial is the degree 256. The ring degree is also 256. It's also not clear how we can apply this technique in our case. So here, yeah, we use power of 2 cyclotomic ring for instantiation. And then we further use the well-known technique used in N-true based, like N-true style encryption, that we use the message to replace a slot of the error. Because in the one-way CPA security, the message is random. So we use it to replace one slot of the error vector. And this is doable for N-true typed encryption. And it's not really doable for like a Kyber LWE base because they plug the message to the most significant bit. But for this N-true scheme, we plug it to the least significant bit. That's why we can use it to replace the error in this way. And we eventually reach as compact as the NEV ciphertext, also with the parameter for the second security level. Other than this try, we have also tried to see if we can use like a entity-friendly ring to further improve it. The motivation is that can we maintain a similar efficiency, but try to beat this ciphertext size? We want to see if this is indeed the limit. So up to our try with entity IO types of ring, it has not been successful. So the most efficient, or say the most compact one, is still given by the power of 2 instantiation. So this all about my work, our work. And for future works, the first question is that our second scheme, we use only the last slot, not all slot. So the other slot is remain unused. So can we make use of that to apply similar technique to double encryption to further make our scheme even more compact? And the second question is about our first scheme. If you remember, we have only one single ring element over a reduced degree ring. But this nice feature comes with the cost that we need to select a relatively large modulus. So it might be fall into this so-called overstretch point for N-true. So we try to use existing resource for original N-true, and our parameter seems to be fine, but it's still not very clear because the existing result is for original N-true, it's not for Module-NTRU. So it's still more desirable to have a formal analysis for Module-NTRU for this overstretch attack. And the last question is simply about instantiation for CCA security. So in this work, we didn't provide such an instantiation. So it would be interesting to see this compact encryption. If instantiated for CCA security, can it be still compact or not? And that's all my presentation. Thank you for your attention.
We have time for a few questions.
Hi, thanks for a nice talk. A lot of nice techniques in there, and maybe it was just that I couldn't follow, but some of them seem to be advantageous for reducing your decryption failure, and some of them perhaps just more generic techniques. Which of these could still be useful if one was aiming only for perfect decryption correctness?
You mean like a perfect decryption error, so no decryption error?
Yeah.
Yeah, if you consider no decryption error, actually, I cannot go back. But yeah, for N-true scheme, actually there are some schemes they consider no decryption error. So in that case, certainly you need a much larger modulus. That you can imagine, right? Because here, all the scheme here, if we want to have a compact ciphertext, we always need to consider like an average noise analysis that, yeah, we need to want a small modulus instead of a very large modulus.
Sure, but would some of these techniques still apply if you were going for perfect correctness? So considering you use a larger modulus anyway.
Yeah, in NEV scheme, they still have this, like with the perfect.
For example, the multiplying by the determinant, this technique, does this give you something that isn't just for reducing like a small decryption failure? Could it be used in a scheme that was also aiming for perfect?
You mean the first scheme using determinant, or?
Sorry?
Sorry, I didn't understand your question. It's about the first scheme about using the determinant.
Some of the techniques that you're using, could they also be used for a scheme that was aiming at perfect decryption without any failure?
I'm not sure. So what do you mean? So again,
maybe we take this up.
Maybe yeah, we can discuss afterward. Yeah. followed.
Any other questions? Sorry.
Hi, thanks for the talk. How does the lattice of this module version compare to the original NTRU lattice?
Yeah,
So
you can
it's,
imagine it's just a double of it. It's like if you choose the rank equal to k, so it's like it's just k times n times k times n. So the basis.
And you have like some results on analyzing if it would be more difficult to solve this lattice instead of the other one? Like
Yes,
comparing the
this is a
security?
very good question. So for the moment, we don't know the module structure can be made use in any sense. So we still treat it as a standard lattice problem. So
Okay.
for example, for like this is a module version of LWE and so on, we still when we attack it, we still treat it as like a standard LWE without any structure because we cannot make use of this cyclic structure in any sense.
Okay.
At least not asymptotically. Yeah.
Okay, thank you.
Okay, if there are no more questions, then let's thank Wei Qiang again.